Okay, good morning all. Welcome back to day 4 of the Nextflow training as part of the NF Core hackathon. We're going to start as we did before, so just make sure that you're logged into the Cloud9 environment. If you want to follow along, there is the password is in the Zoom. There's a question there about getting your environment running out of quota. Please make some space. I haven't seen that before, Shri, but we can get Paolo to have a look at that. Maybe if you share with him the error code, and then you can have a look into that. One thing to note is that make sure that you have you've definitely run the setup script because that expands the space that's available on the VM that we spin up. Okay, starting today. So we saw yesterday that we created this RNA-seq pipeline, which was this one that we typically use for training and also just for demonstration purposes. And that's this one here. We saw that we kind of pulled the end of all of the syntax parts together in terms of this pipeline, and we were adding the separate sections. So we define parameters, how we can define channels and the various processes. And then the key part at the end was being able to pull that together with the use of the operators which defined it. Now, as I said, we're going to change gear a little bit now, and we're going to jump into the section number 8 here, which is managing dependencies and containers. So it's really important to be able to run our pipelines in different environments. We've seen that if you want to collaborate, if you want to scale your pipelines, make them portable. And containers is really the technology which has enabled us to do this. And this really gained some popularity around, I think, 2013, 2014, through the kind of rise of Docker. And these containers were really developed initially for web services. So for developers creating web applications, they could simply spin up containers that would run on web servers. And one of the interesting things that we saw was that if you could take that idea and apply it to essentially bioinformatics tools or even any kind of batch-like computation. So early on, a lot of the tooling around containers this has been done with Docker, and there's some excellent tooling around that. Docker's almost become a kind of de facto standard for containers. However, there is some other technologies around which are similar and have some differences around that, which we'll see later on. So they're extremely useful for us. They allow us to essentially create like a small computer, a small operating system with all the dependencies that we need to run a task in a self-contained approach. So we saw before that these are immutable. This means that every time we spin them up, they actually have the same state as they were from the start. So, and we'll see some examples of that before. There's a little bit of information on the history of them and how they came about from the C groups. What we're going to do is first start with looking at the Docker tooling and see how we can run these containers. And the first example that we run is just this hello world. So to run a container with Docker, we just have this Docker run command. And you'll notice here that this is just saying Docker run hello world. And when we do this, so I'm going to close this here, close this for now. We can see that we get this message. So the first thing that comes up is it says it's unable to find the image locally. So what this means is this is you can think of this somewhat like a repository in Git, or like a Git project. However, it's a container image, and these container images live in a registry. In this case, the registry is Docker Hub, and that Docker Hub is remote from us. So just keep in mind that when we run this, this is not like a file specifically, and this is a container. So what happens first is that it sees that it's unable to find this locally. It pulls it from the remote. When the pull is complete, it gives us the status image. So it's downloaded this image. And then the only thing that hello world does is print this message for us. Hello world is just a example container, and the example container tells us what's actually happened in the background. So this says hello from Docker. So what's happened in Docker, there's something to keep in mind, is that there's two parts to it, typically, or two parts to it, at least on our machine. We have the client, which is the Docker command that we ran, so the Docker command line. And then we also have a daemon, and the daemon is running in the background of our machine all the time. And what this means is that the Docker client itself, when we write Docker run hello world, it contacts the daemon, which is running in our machine. And the daemon will look for hello world and see if that exists. If that image does not exist, the daemon will pull it, in this case, from Docker Hub. And then it's going to create a container from that image, which will be run and executed on the daemon, and it will stream the output back to the client. Now, this has some security implications because you're having to run a daemon, it has to have elevated privileges, and we'll see later on how that can provide some problems. But the key point is that with Docker, we're essentially running daemon, and it's streaming that output to the client, which we're able to just observe here. Okay. This doesn't do much for us. This is not particularly useful for using it in this environment. Let's do something more useful. Let's try and get a more useful container. And you can see in the example here, we can not only run a container, so where we ran hello world, but we can pull containers. So this is a way for us to take the container, which is say on a remote, and pull it to our local machine. And the container that we're going to pull here is just a base image for Debian. So Debian is a flavor of Linux. And then after this dots here, we have the actual version of that we're going to pull. So I'm going to pull this into our here. And this will just take a few seconds. You can see that now we have the version of Debian, and it's available to us. Okay. So that's kind of useful, but now how can we use this? How can we actually use this container which we've just pulled? Well, we could run a container as we did before, where we ran the hello world. So we could imagine doing Docker run, and then we would put in the name of the container, in this case Debian stretch lim. But when we do that, nothing really happens. And the reason for that is that this container, it doesn't have an execute command. Basically what's happening, that the container is coming up. We're not telling it to do anything. So as soon as it's finished, it's essentially going to go down and stop running. However, we can run containers in an interactive manner. And this means that we can you can think of it as going inside the container. And with Docker, we can do this using the Docker run. And we can just use this flag here of IT, and then we can place the actual name of the image that we want to run. So we could run, again, Debian image. And if we wanted to, we could also specify a command to run. Now, in this example, we just want to go into the container. So let's just use bash. So we'll just go inside with bash. First thing to notice is that you'll see that the start here of my line has changed. So now I'm no longer on the host operating system, and I'm no longer Evan. Now I'm root, and I'm on this different machine, essentially. Another thing to note is if I do ls here, you can see that I have a completely different file system. Now I'm in the file system of the container itself. If I was to exit here, and then to show you an ls here, you can see that now I'm back in the host operating system. So this fact that when I'm here, I'm root, has some security implications for running, particularly in shared systems. But we've seen that we can pull a container, that we can run a container interactively. Just to go back from the container, I can click exit, and I can run this. I don't think that this bash is strictly necessary to run on the end there. Okay, So now we can jump into a container. We see how we can run a command, pull it. Another thing that you could notice to see Docker images. And Docker images is a way of seeing the images that I have available to me from my daemon. So you can see that we've got the hello world we just pulled. We have this Debian stretch, which we also just pulled. And you can see the size of it here. And we have the Nextflow RNA-seq, which is the container we were using yesterday. And that container is the one that has Salmon installed, that has FastQC and MultiQC. What we're going to do in this exercise now is build up a container from scratch. We're going to build actually a new container from scratch, which contains Salmon, and we can then use to run our pipeline from yesterday. Okay, so let's build a container. Let's make a container. The first thing we need to know is to build these containers, we use what's called a Docker file. And a Docker file is just a simple text file, and it has a specific naming to it. So I'm going to just create now a directory, which I'm going to call Docker. And inside this directory, I'm going to create a file called Dockerfile. Okay. I'm going to take the contents of this, which is inside here. So this is our first Docker file. I'm just going to take the contents of this and paste this inside this blank file now. Oh. Like this. And let's consider some of the lines that we have here. So a Docker file has a series of commands, and these are all in capital letters here. So the first one that we have here is from. From is a way of starting from a base image. It's essentially saying, I'm going to build this container from this. Now, this is a first hint to showing you that containers can be composed of layers. So we essentially have several layers here, and the order of these commands is essentially a layer that we're adding on top of the previous one. So it's beginning with a base image, in this case Debian, a blank operating system. We can have some metadata, a maintainer in this case. You could put your name, you could have a whole bunch of metadata inside there. And then we also have a run command. So the run commands are probably the most important here. They are what's executed to build the container. And in the first case, you can see that we're just using apt-get update. So, and then installing two pieces of software, curl and calc. So apt-get is just a repository, a package manager that you'll typically see in Linux systems. And we're just going to install curl and calc, two pieces of software. Finally, we can also change the environment. So we can update the path to include this user games directory so that we're able to pull from calc here. So I'm going to save this. And the other thing I want you to note is that I did this inside this Docker directory. So I created a Docker directory to create my Docker file. And the reason for this is that when we now build this image, Docker pulls in what's called the context of the other files that are in that directory. So ideally, I would not want to build my Docker file with, hundreds of gigabytes of files that I didn't want to be inside that container, because they will automatically be pulled into that container context, and then that container would be very bloated. So it's kind of best practice just to pull that in. If you do have to build a Docker file inside another directory, you can use a docker ignore. Now let's build this container. So to build the image, we have a similar command as before. We have docker build, and then we want to give it a name with a tag. So we're going to call this one simply my image. And then we're going to use this dot. Make sure you get the dot. So the dot is saying in this location, and this is why we also created this new directory. I built this image here. You can see that there's the series of steps. So 1, 2, 3, 4, because we had 4 commands. This is running through and just doing the typical install. And then at the end of this, you can see that we've successfully built this image, and we've successfully tagged it. If I now run the command again, docker images, you can see that I have this image here, which has been tagged with the latest, created 12 seconds ago, and this is the size of it. Okay, great. Now, how can we use this? So remember that we created, in this container, we installed 2 pieces of software. And one was curl, which we'll use in a moment. The other one was calsay. So if I was to, for example, now run calsay, which is just it's an application used for testing and training of containers. And it doesn't really do much, but we'll have a look at it anyway. So we can say docker run. We're going to create the name of the image we just set. So my image, the one I just created. And then we can do the application, calsay. Now this is going to now run the calsay application inside this container. And I can provide it with an argument, for example, hello Docker. This is just a argument to the calsay application. Yeah, great. So now what's happened is that the images come up. It's run that application calsay with hello Docker. It's streamed that from the daemon to our client, and then the container has closed. It's gone away. We could also do this interactively, you can imagine. So you can see that, for example, if I run on my machine, if I run calsay hello Docker, I don't have this here. But if I was to say run into this image that we've just created interactively, so again, run interactively into my image. Now I'm inside the image, and now I could use that command. Now I could say calsay hello Docker. Still inside the image though. Exit out of here. Cool. Now, how can we actually add something useful to this image that we've just created? Because that wasn't particularly helpful for what we want to use. Let's consider that we want to now install a piece of bioinformatics software, and let's install Salmon because we were using this before. I'm going to open up the Docker file again. And on the end of the Docker file here, I'm going to install and add another command. So this is taken from here, and we're looking at this. So I'm going to add a software package to this image. When I do this, paste this in here, you can see that this is the command which has been run, and this will be run when it's building the container. And you can notice that you can also have several of these commands by splitting it across a line and using the notation here. So this is going to be downloading from GitHub, and then it's going to move the binaries onto my path. I'm going to save this. And now I can do as I did before. And I had the commands here before I want to build this container. So docker build. I'm going to give it a same name because we want to keep using the image that we've built. And I'm going to specify this location. Okay. Thing to note here is that we have now 5 steps, but notice here that these steps here have been using cache. This is a bit like Nextflow's caching mechanism. Because nothing has changed in the previous steps, we've only added a final step on here. We don't need to build all of the steps again. And this can be very useful, and also in some ways very you can save yourself a lot of time if you have many containers to build, to always use the same base image. And you can think of it as trying to keep the early steps in your building process the same. And this means that you don't need to have multiple copies of them that have to hang around as well as we've been built. There's a question, questions on the side. So does Docker also pull directories? Say if I had a .yaml file under configs and YAML in a GitHub directory, will Docker then build the conda environment if configs with the configs? We'll see exactly how we do that, how we use a Docker file to build conda at the very end of this. I'm not sure if, to be honest, I'm not 100% sure if it pulls directories. I would suggest trying it out. What we typically do though is specify exactly what you want to pull into the container. use it there as a copy command. And again, we'll see that at the end when we use conda. And another question is are Docker images similar to conda environments? Somewhat, but also quite different. We'll come to conda at the very end, and we'll see the differences there, and we'll see how we can actually combine them to very good effect. Okay, so we've now, just recapping, we've built this image. If I say Docker images, I can see that I have this new image, this one I just built, and you can see now the size of it's gone up a little bit. Okay. Now let's start running it. Let's start doing something useful. Start doing some bioinformatics. Okay. How do we check this? How can we confirm? We've just installed Salmon in this container, and let's see if we can run this now. So I'm going to say Docker run my image. And then I'm going to say Salmon, because this is what we need to run. And then I'm just going to use version. This is just to confirm that we've actually installed Salmon. So this, remember, this is going to run up the container image. It's going to run Salmon with this version command. Okay, great. So that looks fantastic. It looks like our container now has Salmon in it, and I can now confirm I don't have Salmon on my host machine. You can see this Salmon is not found. And this is the error that we saw yesterday, if you remember, when we tried to run the first process of our pipeline when we were indexing the transcriptome. And what we're going to do now is run through essentially how we would index the transcriptome with a container. So imagine that someone came along to you and they said, here's this container technology. I want you to go do some bioinformatics with it. We're going to go through the steps of maybe how you would go through this, and then it should help you understand a little bit of the background that's associated with these. So I'm going to say, imagine that we want to run our command as yesterday. If you remember that it was, we can actually look at it into here. This was the first step that we had inside script 2, I believe. We want to run this command. We want to index our transcriptome using salmon index. And we want to now do this inside the container. So inside the container, we want to run this. The first approach would be to simply consider what we had before. Remember that we can run any command. So we can say Docker run, we can say my image. And then we could say, in this case, we could write salmon, because this is what we want to run. And we could actually just copy this command, couldn't we? We could just say salmon index. We know that we have to provide a transcriptome. We have a transcriptome in this data. I'm just going to, if you just hold on a second here, I'm just going to cd back one. Make sure that you are in the base part, the project directory here. So I just have to skip back one. But I say I'm going to go Docker run my image, and then I'm going to say salmon index, and then I'm going to place the index, the transcriptome, which is going to be in our current working directory, and it's under, I think it's under data. Let's see if this is working, data, gggal, and then we also have the transcriptome, so that exists, and I want to create a index. So you can see this line here is exactly the same as we had before. We're just placing the full path of the transcriptome that we want. Now let's try run this. Okay. So we see that salmon is launched inside the container. And at the very end, though, we can see that we get an error. So the file transcriptome provided for the transcriptome, sorry, does not appear to exist, which is kind of weird. So it's saying that this file here does not exist, which is weird, because if I was to take this here and I was to say ls on this location, you can see that the transcriptome does exist. So something weird is happening here. And the reason that it doesn't exist from the container's perspective is that, remember at the start, the container has its own file system. So the container in this way is not able to access the file system of the host. So I'm the host here. I actually have that location. As we can see, I have those files. But when I'm inside the container, I cannot access them. So one way to get around this is to simply mount the host file system inside the container that we want to use. And we can do this using the volume command. So we can do this by saying docker run, and then you can use volume here. This is a way, an option in Docker of mounting what we had. I'm just going to copy paste this because this gets a little bit long. But what we're saying here is we're going to say docker run, mount this volume. The volume that we want to mount, or the path that we want to mount here, is the transcriptome file. This is the location on my host. I want you to mount it inside the container here at this location, so just in the root folder. And then I want to do the same as before. So it's my image, salmon index, specify the transcriptome. Note this is now the new location inside the container, and then the index that we're creating. This can be anything. Great. So that looks like it's run. You can see that it looks like it's run the salmon index step. There was no errors, I don't think. So there's no errors that have run. And we should now have our transcript index that we've just created. But where is it? You can see that I was supposed to create this file here called transcript index, but now it's gone. It doesn't exist. And the reason it doesn't exist is that the container came up, it mounted the transcriptome, created the transcript index, but then as soon as the container left, as soon as the container went down, that transcript index was lost. So the container is immutable. You cannot change something on its file system. Every time you bring it up, it's lost. Okay. So how can we deal with this? Well, one way that we could deal with this is we could actually mount not just a single file here, not just the transcriptome, but imagine that we mounted here our whole home directory. So let's now mount the whole host file system, or at least the home that we have. And let's place that in the same location. And this should be like kind of creating a mirror of our host file system inside the image. And this means that then we're then able to access that in the same location. We can also provide a working directory here, which is just saying, okay, do this from this location. And we're just going to say, this is now specified in the host. So do this from here. So we're going to be running this command from this location. And that will enable us to then, when we run this transcript, we can specify now the full path that we had before. So I'm going to say, just take this, and then the rest is the same. So now I'm going to specify the full location. So the reason I can specify the full path here is because now I've mounted my whole host file system inside the container. Okay, let's try run this. Great, so this runs. This is fantastic, same as before. It looks like it's all launched. And now if we do ls on this location, you can see that we've created this. So we can see that we've now created this transcript index. This is the same files that were created from our exercise yesterday, and we now have an index of that transcriptome. Perfect. We're in business. However, there's one other thing to check here. Remember how we said that when we run in the container, we are root. However, if I say who am I? I'm EC2 user. If I do ls onto if I do this on transcript index, notice that this transcript index has been created as root. So if I do this on this folder here, notice that all my other files are EC2 user. They're mine, essentially the user that I am in the host. But notice that transcript index is root. Okay. This could cause some problems. Imagine that I want to remove this. I'm not not able to. Permission denied. I don't have permission to even access that, because as far as the host is concerned, those were created by root. And you can see here that here are some of the problems that arise from using Docker in shared systems, because it allows you to elevate your privileges to root. And therefore, I could do things malicious if I wanted to in a shared file system. And it's for this reason that other container runtimes and container systems have become popular when used in HPC, when used in shared systems. There is a way to avoid this, and we saw this in our Nextflow config yesterday. If I do a cat on the Nextflow config, you can see that we provided a run option to Docker. So this is, and when you run with this, Nextflow injects this option into our Docker commands. We can do the same thing here. So I will run now the same thing. I will just firstly, I will remove this so that it makes, I can do sudo here, but typically you would not be able to do this in a shared system. So I'm going to say transcript index. I can remove that. Now I'm going to run the same command as we had before, and I'm going to provide a Docker option here. So one of the core Docker options I could provide would be change the user who I am. So when I change the user, you can see that this means, okay, use the user that I am in the host and use the group that I am in the host. Launch this. Oh, what happened there? Something weird happened there. Not sure why that was the case. I think I may have, I forgot the U. That's right. There's a missing U. So it was trying to find a container called U. It was just a typo. There we go. And now when I see this, if I do lsrt on this location, you can see that transcript index is now EC2 user. Something to keep in mind when you're doing this. Okay. I would say though that, I mean, all of this that we're doing, this is not the way to run bioinformatics in containers, of course. And this is one of the big benefits of Nextflow, is that we don't have to deal with all of this crap and what simplifies it a lot. But it helps to keep in mind what's happening in the background and what's really happening to get a better understanding of this. Another thing that we can do is that we can see we created this container before, and you remember that we were able to pull the local one. So we could pull pull the remote. So we were able to pull Hello World. We were able to pull the RNA-seq yesterday. And the way that we can do that is with what's called container registries. And container registries are a little bit like GitHub, or Git hosting solutions, which are obviously for code repositories. These are container registries, container repositories, you can think of them. And the default one, the kind of one that sort of comes prepackaged, you can think of it with Docker, is Docker Hub. And you can create very much like GitHub, you can create free accounts here. And if you're providing that your images are, what's it called, open, then you don't have to worry about the paying for these. So this can be any free image which is open to the publicly available. Let's see how we can do this. So here is my Docker Hub login. You can see I have a few random containers here. You can see I have some organizations that I was part of. What we can also see here is how we can now both push and we've seen how we can pull, but how we can push these containers. So you can use Docker login here. It'll ask you with your name, so to log in, and your username and your password for doing this. And once I'm logged in, now I'm able to push the container that we had. So remember that on our local, we have these images. And I want to now push this to my registry. And the way that I have to do that, I should provide it with the actual name of my registry before the actual name of the image. So notice how that this one is living in the Nextflow namespace from here. I want to do the same thing, but I want to push this into my name. So I can do this by changing the name, by giving it a tag. So I'm going to say tag my image. I'm going to give it my name, and I'm going to give it my image. What I could also do here is I could give it a version, So I could use the colons to say, I want to give this one version 8, for example, whatever you want. By tagging this image now, I can push it. So the same commands. So Docker tag, now I'm saying Docker push. I push this image. Takes a few seconds. And once this image is pushed, now any of you can use this. So anyone in the world now can just say, and you can try it if you want. If you just say Docker pull on this namespace here, you'll be able to pull my container and you'll be able to use it. And you can just see how powerful this is in terms of being able to share dependencies and share software and ultimately share our pipelines because it becomes just so simple to handle all of these dependencies. So you can see a few seconds ago, this was done. I have this tag, which was just pulled here. And then, of course, you can get all sorts of tooling around this to, for example, be able to build these containers automatically. And that's some of the things that we're really interested in, is building these things on the fly, the security associated with each container image, being able to have a container image connected to a Nextflow process, say, and automatically run unit tests based on that, the security associated with these. There's a whole bunch of really exciting work, which I'm sure is going to go on over the next years to really build on this excellent kind of base and keep moving this forward. One thing you might notice there is that you also, when we do this, we get this hash. So this hash on this tag, you can see it. This is a specific hash of the contents of the container. So, unfortunately, or fortunately, some of these things, these tags are not immutable. So I can actually rewrite over an image with a tag. However, the hash here is unique. So if I change one byte of information inside of that container, this will change. And this is a kind of very useful way if you're really focused on the reproducibility aspect, that you can tag, you can have your images and you can actually call them from Nextflow as well, and also from Docker, obviously, to run with this specific hash. And this is a kind of a fingerprint of the contents of that container. Okay. How can we use this with Nextflow? How can we use our containers that we've just built, and how can we use them to run with Nextflow? Well, we saw a little bit yesterday how we can run our pipelines, or run our pipelines using Docker. And what we're going to do now is just run the script too. So we're going to run this exact script that we have above us here using the container that we've just built. So I'm going to say Docker run script 2. And I can now say with Docker, as we saw yesterday. But I could also specify here the image that I've just created. I could say, if I wanted to, I could say the full path of the image here. And this was like this, and then it was my image. And you should be able to do the same here, my image, for example, version 8. I can specify this here at the command line. I could also put this in the Nextflow config, as we saw yesterday. I could even go to the point where I could specify this for a specific process. But for now, we can say we can run this container that we've just built. We're going to launch script number 2. And now it's built with the container. So let's just run with the container that we have just built. Let's go a little bit into the background as to what's happening here though now, because we should be able to appreciate what's gone on in the background and why Nextflow is making this so easy for us. So if I take this work directory here, this 1FC7 in my one, I'm going to copy this. If I go inside the work directory, so I'm going to go into the work, go into this folder. Remember from yesterday that we have a series of commands that are inside here. There is the .command.sh, which is the command that's actually executed by Nextflow. You can see that one here. So this is salmon index with the number of threads, etc. As we've changed this inside here. We also have the other kind of important one, what's actually executed, what's really going on in the background, the kind of I guess, secret source to us. Streaming on my phone now. Hopefully you can hear me. Okay. Great, fantastic. Let me just share my screen again here. Okay. Apologies if the connection might not be so good. I'm on 4G now. Let's hope. Okay. So remember that we might want to run this. We want to now run this exact same thing that we had before. So we want to run the script with Nextflow. And now we wanted to see what was inside this working directory. So remember that we have these series of commands. The .command.sh is what we're launching. I want to now look at the .command.run. So let's consider this. Let's do a cat now on the .command.run. This is what Nextflow is actually doing when it launches a script. So this is obviously specific to the execution environment. Here we're running locally with a container. So it creates some container environment. The key thing that's important here is the actual launch. So what is Nextflow running? You can see that for every task that we launch in Nextflow with Docker locally, we get this Docker run command. It mounts the volume for us. It mounts the working directory we have. It creates the work directory at this location. It creates an entry point, which is bash for this in this case. We already fixed the user environment because we specified that in the options. We run this container image, and then we do some various things here, but the most important part is then we actually run the .command.sh. So all of this actually happens for you in a kind of transparent manner. You can see what Nextflow is doing here. But doing this to yourself for every task, if you had tens of thousands of tasks, would be really annoying and kind of difficult to do. So if you want to dig into what's actually happening in the background, check out that .command.run, and then I think you'll be able to appreciate a little bit more of what Nextflow is doing in the background there. Okay. Cool. Let's consider now something else outside of Docker. So we've seen all of this. We're going to now skip to or jump to how we can use Singularity. So Singularity is very much similar to Docker, except it does have some differences. And these key differences really come around how you can use it with a shared file system and the permissions that are required to run Singularity. So Singularity is no longer, it doesn't have a daemon and a client. It's just a single file which can be run. And Singularity images can also just be single files themselves. So if we were to, for example, build a Singularity image, they have a very similar notation to what we have with Docker. So we have you can see we have the same from command. We have an environment variables, which we can set. We can have some metadata, there's labels here. And this post is the equivalent of the run that we saw in the Docker image. So I'm just going to quickly create a Singularity file now. So I'm going to make a directory, Singularity, cd into that. And then I'm going to create a file called Singularity. And then inside there, I'm going to paste the same stuff. So this is going to create effectively the same image as we had before. We can see that we're installing curl, calce, etc. Post this one here. I can now build the Singularity image using a very similar command to what we have before, except instead of now Docker build, I'm going to say Singularity build. And the one thing to note here, which is kind of annoying, and kind of why we don't do it this way, is that you should be sudo if you want to build the image itself. So sudo to build the image, but not sudo to run it. So the command here is sudo singularity, build this image. Notice that now it's actually a file. I'm building this file itself, and I'm going to base it from the Singularity file I've just created. This runs through here. It's going to do all of the steps that we had from before and build our Singularity image. So there's a few differences that we'll observe now with this singularity file that we've just created, because now it is a file itself. We can execute the commands inside that. So if we look at here, once we've built it, we just say execute itself. This is the same as just the normal run command in Docker, where we can provide the application we want to run, and then we've got an argument here, which is just hello singularity. Wait for this might just take a few moments to actually create the image itself. And then we also have the shell command, which is the equivalent of running interactively. This is the equivalent of us saying like IT into that. So once this is built, I can run this where it just runs the commands. So what's happening here, we're launching this, the singularity container is coming up, and then it's able to run through here. And then there's a question here. So what is the last singularity in this code? Pseudo singularity. So when we built this container, this is actually the file that we have here. So this is the singularity build file, the equivalent of the Docker file. If I was to look here, for example, this is just this file here. And notice that we've now created from this singularity build file, we've created this SIF image. Cool. So we can execute. This is us. This is, you can think of this as going into the container, running the command count, say hello singularity, and then the container comes down. We also have a way of running this interactively. And this is this command here, singularity shell, the name of the image. And when we do the singularity shell, we go inside the container and we're now inside here. There's just a few errors here on the thing, but you can see that we're inside the image itself. And the thing to note is that now that we're inside the image, it's a little bit different from what we have from Docker. So Singularity automatically mounts the host file system. And if I was to say, who am I here, you can see that I'm actually EC2 user. There's just some errors on the screen here. I think that there must be an issue with the way that Singularity is installed here. So you can ignore this part, but you can see that we are EC2 user in this thing. I'm no longer root or etc. So this has some advantages, and it means that when we run our applications with the Singularity command, we don't have to worry about the permissions associated with it, because we are running Singularity as the user that we are, and with the group that we are. Same thing with creating the files. So if I was to go inside here, I will exit out. Or if I was, inside this container, and I was to say, okay, let's create a file here called touch.txt. Now, if I was to do exit out of the container, you can see that this a.txt was actually created inside the container, but it has the same user spaces as me and the same permissions. So you see this has some advantages. The really cool thing though, and the reason why this is, this is the reason why I think this whole system works so well, is that there's interchangeability between them. So from Singularity, I can run Docker images. So I can use this command here. For the first case, I can pull from Docker Hub, and I can pull from Docker Hub and create a Singularity image. This means that in reality, it's almost certainly better. It's almost certainly recommended to build containers using the Docker build tools. So using the tooling for Docker. Because if I can build my tool with Docker, then people who are using Docker in the cloud or locally can use it. People who are using Singularity and HPC can use it. And there is a kind of full compatibility across this. So if I now look here, you can see I've created this Debian stretch from Docker Hub. This has some cool benefits for us, which we'll see at the end of the session. So I can also take the same philosophy that we saw before with running Docker with Nextflow, and I can use Singularity. So now let's run script number 7. I'm going to load this up here. You can see that script 7 was actually the complete one that we had. It's running all of the steps that we want. Or we could even run script 2, however we prefer. But let's run script 7 because we've got everything in there. If I was to run this with Nextflow, and then we can see the differences here. I could say, for example, I could take my Nextflow command, which we have here, Nextflow run. I'm going to say script 7 with Singularity, and now I can specify a name. Now, what we're going to specify here, this is actually a Docker image. So this is going to Docker Hub and pulling this, and we'll convert it to a Singularity image automatically for us, and then run all of the tasks inside this pipeline as Singularity exec commands. So from the user perspective, we don't have to worry about this so much, but we can just run like this. Okay, this is because I'm specifying here with Singularity, and inside my config, I'm telling it to use with Docker. So I'm just going to say, check out my Nextflow config here, and I can just remove this for now. We'll go back to the Nextflow config after the break. So I'm going to run script 7 here. And you can see you get this warning image that says that I haven't defined a cache directory for Singularity. So with Singularity images, you can define a location where they all get stored. This can be super useful for if you are in situations where you want to, for example, have a group of people who are all working on a shared file system. They can all place their images in one place. And then if other people use them or you use them across different situations, you only have to have one location for them, so the images don't have to be pulled all the time. And sometimes they can get quite large, several gigabytes for big, fat containers that you're putting, tens of tools inside of. So something to keep note. What happens here automatically is that Nextflow will create a directory inside your work directory, so a place inside work called Singularity, and it will use that as the location to store the image that's been created for you on the fly. So this will take a few moments to load. I think while this goes through, we'll take a short break, and then we'll come back at 38, so in 10 minutes time, and we'll finish up with Singularity because we're just about there. We'll have a quick look at at Conda, and then we'll see how how we recommend that you actually build your containers, kind of pulling all of these three things together, and how this works. Okay, so I'll see you back at 38, and then I'll also answer those questions then. Okay, thanks for bearing with me on that one before. So we saw that command now, that the execution that we had before is just now launched, it's finished, and this is running with the Singularity that we said before. So if I now look into this location inside the work Singularity, we can see that a Singularity image has been created, and this was pulled from Docker Hub, remember. Likewise, if I was to do, I just want to check the actual location of that, location of some of those tasks, so we can see what's happening for each of those. So one of those tasks there was, let's look at this. So now if I was to go inside the work directory into this one here, and I was to look at the .command.run, you can see that instead of having now Docker run, we should have a singularity launch command. So you can see that here we have singularity exec. So as you can see, the Nextflow has been able to take care of that for us and run singularity. Let's go back a few here. Right. Similar to Docker Hub, there is also Scilabs, so is a company which is responsible for some of the work on singularity. You can find information there. They have a whole bunch of services, for example, for storing your containers, for signing them, and of course, providing support around the Singularity engine. If you're interested there, you can check out some of the hosted cloud, for example, for pushing your Singularity container images. Okay, let's jump slightly to the side now and consider conda. So with conda, it's not really a container engine. So now conda is much more of a traditional package manager. And the reason that we're so, why conda has got so much, so much love recently is essentially the way, because of, in bioinformatics anyway, because of bioconda and the way that the community has really rallied around it to be able to provide so many of the key tools that we use and that we love, that we're able to be accessible in this manner. So let's go have a look at bioconda itself. So bioconda is a channel of conda. And you can see that here, I always lose track of how many we've got. So we're up to now over 7,000 bioinformatics packages. So all of the main software that you use. And if you create your own software, of course, you're very much encouraged to provide it as conda packages. It simplifies the installation. And we'll see in a moment how we can use this to use conda to actually build our containers as well. We can use conda with Nextflow at the same time. So with a conda environment, we don't have a build script or anything, but we have what's called a conda environment defined with a YAML file. You can see that this is an example of one here. We provide a name. We provide some channels that we have, so defaults, bioconda and conda forge, and then we can list the software that we need that's kind of going to go inside this conda environment that we're creating. So this one here, we can create a conda environment with conda env create, and then we provide a file. What I would say is that sometimes this can take a long time, depending on the number of dependencies that you have and how kind of complex that dependency tree is that you build. So take note of that. In this tutorial, you can do this if you want, but we're not going to go through this because sometimes it can take 10 minutes or so to do this. A few of the key commands for running this, so you can see that we can do, cancel on this, we can do conda env list, so list the environments that are available to us. You can see that we are running the base conda environment. If we were to create a conda environment, say we created this one here, which would be now NF tutorial, we could then activate that conda environment. And once we activated that conda environment, we could then use that natively. So use that from the command line. We would have, for example, salmon available to us. Nextflow is able to handle this activation of the conda environments, and actually is also able to handle the building of these conda environments for us. So you could run, for example, if we were to create this one here, we can try to do this quickly, but I'm not sure if it's, I think that we have this available to us already. If I was to, for example, see on this cat.env YAML, you'll see that this is the same file that we have. I could then try and build this, but I think it may take some time. I'll try and make this run for a few seconds. I haven't actually run this in a while. Sometimes they say that it's been getting quicker, but I haven't seen this. The key point is that we can use conda in the same way that we can use Singularity and the same way that we can use Docker. So we can say Nextflow run with conda, and we can specify the conda environment that we wish to use. And what will happen in this case is that Nextflow will activate that environment for each task that it launches with conda. It will run conda inside that environment. and then it will deactivate it, of course, or just run simply inside of that work directory. And solving environments is not particularly fun, so I think you can trust me that that works. Follow along outside if you wish. Okay, but I say like I think that the main point that we want to make here and sort of how we do this is that we can pull all of these together. We can pull conda, singularity, and Docker together in a way. This is what's done with the NF core pipelines as well. The way that we want to do this is we want to take advantage of some things. So bioconda is excellent in terms of the number of resources that it has. How easy is it to install multi-QC if you just have to have one line in some dependency file? We want to take advantage of conda in this. We also want to take advantage of containers, because containers are much more portable. They're quicker to bring up. They're a little more you think of them as stable than conda environments. Certainly more portable. And we also want to be able to have users who are using shared environments and HPC to be able to use singularity. So we want to take advantage of all of these aspects. And the way that we do this is we build our containers from very basic conda files. So we define, for example, in this RNA-seq pipeline, the same pipeline we've been using. We create an environment. In this case, this is RNA-seq for conda. We define the dependency, salmon, multi-QC, fastQC here. And the magic is that inside of our Docker file, it's just a few lines, but inside of the Docker file, we're actually creating the conda environment. And in doing so, now the container, we now have a container which contains the conda environment. So people who want to run Docker can use this. People who want to run Singularity can also use this because of the fact that Singularity can pull Docker images. And we also have a conda environment for people who have to use conda themselves. So we're providing the use case for all of these. The question about can we activate environments for each process? For containers, for sure. For conda, probably, but let's skip that for later on for the config. We'll see that. Maybe Paolo can answer specifically on conda environments. For containers, but we'll certainly see it in a moment. So this is the kind of recommended way I would do this. You can literally just copy this file. This is really all you need in your Docker files, providing that you have your software in bioconda, and then you can pull that. Another consideration here is what should you do in terms of the container makeup. There's a couple of options. So you could think of it that you imagine that we had in our pipeline here, and in the script 7, we've got a couple of dependencies. We've got this process which runs with salmon. Okay, that's fine. We've got this process which runs with salmon. This is the quant one. That's fine. We've got this process which uses fastQC and this process which uses multi-QC. Now, the option and the thing we've done here is we've built a single container. And in that single container, we're placing all of the software that's required for this. But you can imagine a situation where I just build a container that only contains salmon. And then, for example, I could specify just here, I could say container, my salmon container, whatever you wanted. And then I could have this one could then use the same one, the quantification, because it uses salmon. But then for fastQC, I could also have like another one. So I could say like container here, and I could say my fastQC container. So this kind of, either contrasting this with like a fat container where you've got everything in there, or a slim container where you are having a tool for each. This is particularly changing as well with DSL2, which is coming out, where we kind of modularize the pipelines. And my preference is sort of changing much more towards having single containers for single processes. And just as the tooling is becoming better as we're developing systems which can handle these, it makes a lot more sense and is a lot more manageable. Particularly allows your pipeline to be reused, or components of your pipeline to be reused in a much simpler way. Okay. So we saw before a little bit on Nextflow configuration. That's the kind of end of the container sections. And now we'll go into a little bit more into how that we can define the Nextflow config. So by far, the most of the time we've spent has been on the Nextflow scripts, this .nf scripts that we've seen. However, there's a whole other aspect of Nextflow, and something which we try and keep decoupled from the Nextflow script as much as possible, is the configuration itself. And the first example we saw was this nextflow.config, where we defined the docker.enabled equals true. Remember that we didn't want to place with Docker in our command line every time. We wanted to say docker.enabled equals true, and we placed that inside the Nextflow config. There's a couple of places that Nextflow will look for the config though. So the first place that we'll look for it is inside the project directory, the directory where we're launching from. So if I go back into here, let's remove this so we can actually launch some stuff. Make sure I haven't got too much. So if we see here, this is our pipeline. And we're launching this. Let's just check this. Okay. If we were to look inside our Nextflow config, at the moment we have nothing inside there. I cleared it out. There's nothing there. But we saw that yesterday that we could say, for example, we could say Nextflow run. And we would say script 7 in this case. And if we just run this like this, Docker is not enabled, so the image would not be able to find the container, but we could say with Docker, and then we could specify the container that we built. So in this case, we're building a container, which is, we can build it from, sorry, let me just check this, inside the Nextflow config. So the Nextflow config has a bunch of options there. We're going to build this up slowly and understand exactly where they come from and how they came about. So from the command line, I would write this if I wish. Now it's going to run this process here with this container. I could switch this out and place this in the Nextflow config. And the first place it's going to be is nextflow.config. There's a couple of other places that you can have a config though. So you could have a config not just in a file inside the current directory. You could also have a location inside your home. So inside your home.nextflow/config, notice this is not nextflow.config, but it's actually just config. It will look for a file there, and anything inside there will be imported into and will be used as part of the config. The reason for this is that there may be some settings that you want that are specific to your environment, to your run, that you want to always import into Run Nextflow. So you can keep some common things there to the environment that you're launching from in that location. A third option exists as well, and that is to actually provide a config file at the command line. So this is with -c config file, you're able to specify exactly a specific config to pull in when you run with that. Okay, so let's start building this thing up. I'm just going to pull this up on the side here so we can view this like this. So the first one that we saw was docker.enabled equals true. And we can see that when we look at the ways that we can write the config syntax, we simply have a name. We have different values though. These values can be integers, they can be booleans, but you have to take note is that, for example, this is different from true. Now it's a string. So keep note of that when you're doing this. We also have some scopes, which we'll get into in a second, how that works. The great thing about Nextflow config is that we can actually write kind of code itself or expressions itself inside the config. So in this case here, you can see that we're defining a variable in the config, property1, and then we can actually use that property inside another config itself. And you can make these as complicated as you like. So you can actually write full expressions inside the config, which we'll see. There's also comments inside these. Again, this is the same convention that we have for Nextflow scripts. So single line comments, multi-line comments, and have a concept of scopes. So scopes are a way of organizing your config into blocks, and we can write this in a couple of ways. Notice that here we have docker.enabled equals true. This is under the Docker scope, but I could rewrite this, and it would be the equivalent for me to do this. Now, when I run like this, I could have multiple Docker options that would be available in this scope. You can see here in this example that another one of the Docker options that we ran and that we have was, for example, let's pull this up and bring up the documentation. It will make sense. Under the, for example, the Docker scope that we have here. So I'm going to now configuration, scopes, Docker. You can see that we are using enabled equals true. Another one that you could have is fixed ownership, which is the same as that we had before with the run options. So I could add another scope, another option here as part of that scope. So by saying fixed ownership equals true. This allows us a kind of a nicer way than having to write Docker twice here, for example, without having to say. It allows me to put a few options all together at once. Okay. One of the more useful scopes that we've seen is, and a kind of special one here, is the params. Remember at the very start, we were looking at just parameters which we can define, and we can define them in several places. So parameters can be defined in a config file like we have here. So let's place this inside of our Nextflow config. This is the config file. We have params.foo, params.bar. We could then, for example, we could say inside our workflow script, we could have params foo and params bar printing both of those. And here we should get an understanding of, let's just create a new file here called, with this contents. Let's say this as foo.nf. We should get an idea here of the precedence which is happening in terms of our config. So if we were to run, save this, Nextflow run with foo, what happens? You can see that it's the first case, it's trying to run from the foo.nf. However, it's been overwritten by what was in the config file. If I was to tab this out, if I was to comment that out, was to run foo.nf, here you can see that the precedence, because there is nothing in the config, the definition inside of the workflow script itself takes precedence. However, there's another one. If I was to, for example, take here and was to say, for example, Ola, and then I was to say, window, you can see that the command line parameters took precedence over the config. So keep note of this order. And the idea is that in the script itself, you would have very basic ones that run. In the config, you'd be able to overwrite that. Maybe the config is something which you run in a specific environment or a specific run. And then from the command line, if you're really going into those details, you can overwrite it from there. Okay. There is the env scope, and the env scope allows us to define some environmental variables that will be used. So we could do the same thing above. If I was to place this inside my Nextflow config, let's go back into here. This is going to define now some environment, an environment variable for alpha, environment variable for beta. when I now launch a process, remember that when we're launching this process now, this process here, this process is occurring possibly in a distributed. This could be, for example, happening in a cloud. This could be happening inside of a container. And what the env scope enables us to do is actually inject that environmental variable in the location that we are running this. So let's run this again. Actually, we should just process echo equals true. You can see that we're able to take, in this case, it's the it's some value, and then it's the home of that, and we're able to run that inside of this task, and then we're just gripping that. You can see that we're able to capture that from there. Okay. The config for process. So we touched on this yesterday, and this was when we looked at the process directives. And the config process is exactly the same as that. It just allows us to define what these process directives are inside the config. So this can be a little bit confusing, but I'll just show you here. So inside of the config scope, we have process. And all of this is doing is it's the equivalent of us being able to define some config for a process, which is what we call directives. And if we look at the directives inside process, we remember that there's all these options that we have for a process. So some of the key ones we looked at before were CPUs, for example, for memory. And going back, we can also define these things. We don't have to define them inside the process itself, so inside the Nextflow script, but we could define them inside our Nextflow config. So this could go, going back, this is Nextflow config now. Just keep that config file there. If I say I want to use 10 CPUs and I want to use this container, I'll just remove this. I don't want to download the container. I want to now run this process here. Let's get rid of this. Okay. What we're going to see happen now is that this process will try and run with these settings. So save this, and run foo. Now this should hopefully fail, I think. Yes, and it fails. And the reason for that is it's requested 10 CPUs, whereas only 2 are available on this machine. You've got to think about the abstraction here. So let me just put this down into something I'm pretty sure I've got on this machine. That by able to define this in the config file itself. There we go. What's happened here? It's because I've no longer defined these things. Let's just say. This will now launch with those settings. So this is kind of basic from when we're running locally. So when we're running this thing locally, this is kind of just going to tell Nextflow to do that. But it becomes very important when we want to run with containers because we want to specify the resources that a container can use when it launches. And when we want to run on cluster, we need to define the resources that we're going to request for each of the tasks that we have for the job submission, and particularly in cloud, we need to say which resources are required for that, and therefore which VMs will be spun up, for example. Have a syntax for inserting all of these values. So you can see here whether you're dealing with memory or time, you can see them in this way. And because these things can be dynamic, we can actually assign them in a dynamic way. So let's consider that I had something like this. Let's go into my config, and I'm going to define that my CPUs is 1, and my memory is 4 times the amount of CPUs that I have. This task.cpus is a way of accessing the actual value for a particular task. I can use it in my config here, And we also saw before that we could use it inside the script itself. So I could say echo using, and then I can say task.cpus. And I can say I'm using task.cpus and $task.memory. See if this works here. What have we got wrong here? Okay, I'm requesting too much. So I have to say 2. These machines are pretty low level, to be honest. Oh, task is unbound here. Task.cpus, task.memory. Task.memory, task.cpus. I'm not sure if this should be. Hello, can you help me out here? Task.cpu, this is inside the command line. I'm not sure about this one. I'm not sure why this is not working. We saw before in this example that we were able to access it with task.cpus here. So this was being able to pull in both from the process directive and the Nextflow config itself. I'm not sure why I can't get this here. We can come back to this. Maybe Paolo will help in a moment. The key point is that we can have this dynamically done. Wrong quote type. Ah, fantastic. Yeah, that was right. We were using the single quotes there. Tripped me up. Twice in this course we've done that. Oh. Okay, now you can say I'm using 1 CPU and 2 of memory. If I was to, for example, change up my code here and I was to say, okay, 1.5 here, and then I do 2, you can see that we can create this expression. Now this is kind of trivial, but imagine a situation where I wanted to do this much more complex expression, where I wanted to, for example, use task attempt. So we can know how many times we've tried a task, and then we can, for example, multiply the memory by this. This allows us to increase the resources for every time that we try it if it fails, and we'll see that in a moment. Okay. This is some more examples if you want to have more complex definitions or more complex values. For example, in a pod, you have to define a map object like this, and the same thing going through. We saw a little bit on the Docker configuration, so we can have docker.enabled equals true. We can define a process.container. So note that the process.container is a directive specific for that process, whereas docker.enabled is part of the Docker scope. And the same thing here for the singularity scope. That the process, the actual container sits under process, whereas the singularity sits under its own one. And this is quite useful because it means that we can define a single container and that we can switch between Docker and singularity without having to change the container out there. So here's of the different protocols which are supported inside Singularity. So library is taken from the Singularity library. We have Singularity Hub. This is the one we used before, pulling from Docker Hub. And then this is to pull from a local Docker daemon. So if you have Docker installed and you wish to convert it to a Singularity image file, you can use this. I think we've seen all this before. This is from above for running our scripts with Singularity, same as before for running our scripts with conda. Okay, now let's kind of put this into action, because the vast majority of the time when we're talking about config, we're talking about deployment, and we are trying to keep the fact we have our workflow script, which contains the logic of our pipeline. It contains what's actually going to be run, the tasks, and then the deployment is really much more focused on the infrastructure. And that's why we kind of keep these two things separate. So by decoupling them and by using a config, which is specific to the execution that you want to do, you're able to keep all this portability. So our script remains the same. We change it via config. The most basic way to change up the scheduler, for example, or the location is the executor. And the process executors that we have available to us are all of the traditional batch schedulers. So I'm going to now go see in the directive executor. This is kind of the main options that we have. So we have local, which is default. So local is just where the Nextflow script is launched. Sun Grid Engine, Univa Grid Engine, LSF, Slurm, PBS, PBS Pro, Mo, HT, Conda, this is NQSSI, Ignite, which is no longer really used that more, Kubernetes, AWS Batch, and Google Genomics. This is actually Google Life Sciences now. So in the same way that we can split up a specific container for each task, we can also say for each task to run on a different executor. So you could have some of your pipeline running locally and some of your pipeline running on AWS Batch, for example. And when we look at the executor, we can control this from the config with, for example, process.executor. In this case, let's use Slurm. So I'm going to now define a process in my config. And I don't have Slurm installed on this, but for the purposes of this demonstration, it should be fine. So I'm going to define that I want to use Slurm. I want to use 2 gig of memory. I want to have 30 minutes, and I want to use 1 CPU. I'm defining this in the config section. In my Nextflow foo, I can say I'm going to use this. Let's say this should all be fine, and I'm going to run now again here. So what I want to see here is what actually is happening when Nextflow is trying to submit a task to Slurm. So this is going to fail because I don't have Slurm, but we can go in and see exactly what's happening. So it fails because it doesn't have sbatch. Sbatch is the command which would submit this to a Slurm cluster if you were connected to one. I'm going to go into this work directory here. So see, I'm going to go cat the work directory of 05, etc. And I want to look at the .command.run. So what's Nextflow actually submitting here? You'll see that at the top of the nextflow.command.run, this is exactly what you would do if you were to submit a script to sbatch. Now you can see that if you see that this is doing, and it's inserting the options which we've specified, and it's doing the conversion of it into what Slurm expects. So Slurm expects our memory of, go back to our config, our 2 gig memory has to be submitted like this. Our queue has to be submitted with this -p command. The time has to be submitted like this. And Nextflow is doing this conversion for you. So it's actually taking care of this job submission, so you no longer need to think about that. What I was to take this out now is to say, let's do this with Sun Grid Engine or AWS Batch. It doesn't matter what I run here. If I run this command now, again, it's going to fail because I don't have Sun Grid Engine. But if I were to look now again into the thing, you can see that now our whole nextflow.run command, what was actually submitted to the cluster. Let's go work on 69 and .command.run. Let's take a look at this. And here, now you can see that this is what Sun Grid Engine expects. Completely different syntax here. It has to be defined in a different way. But it's able to do that conversion for us. But note that the abstraction from our perspective in terms of defining CPUs, in terms of defining memory, in terms of defining a queue, it all remains the same for us. So the user is able to very quickly take your pipeline without having to know the specifics of each environment, right? Or how each system operates, and is able to quickly take the same pipeline and run it anywhere. Okay. We can see that for cluster resources, there's some common ones which are used. So you have a concept of a queue, CPUs, memory, time, and disk. Let's imagine though that we wanted to run different processes with different resources. So going back to our example, let's say that we had here, we've got foo. Now let's do bar. Okay, and I'm going to say, put here foo, so we know which is which, and I'm going to say, okay. So now we're going to have two tasks. And imagine that in the first case, this one here required lots of resources, lots of memory, and the other one required lots of CPU. So let's go back to our config here. I'm going to take this example that we have before. And I don't want to run with Slurm, but I'll just run locally. It should be the same for the thing here. So inside the config, I'm going to say, take all of this the same. This would be like the default options if I don't have a specify with name. And what with name is doing is this is saying, okay, if there is a process which matches this, then use these options. Fairly straightforward. Imagine that one, in the one case it needs 1 gig, and the other one it needs 2. And it was submitted to a different queue, for example. If I do this and now run locally, you should be able to see that this comes out like this. And you can see that foo was using 1 CPU, 1 gig of memory, and bar was using 1 CPU and 2. When you say, so there's a question here, when you say matches, is that equals or contains? I think this is, in this case, it is equals to. It's equals to. We'll see in the next example, though, that you can use labels. So in this case, to use this config, the process has to contain the name foo. Same with this one, it has to be called bar. However, it may be more convenient for us to actually create labels. And labels are a way of composing many processes into a single kind of group of config. You can think of it like that. So imagine that I have a label. Let's go back to our example. This is like let's go back to the code. If I say this would be, for example, label is, let's imagine this was a small task. So this was like, instead of being on the long queue, I'm going to say that this was small. And then this was big here. So I would do the same thing here. Just put label but big, say this, go into my Nextflow config. I could define a label of small. So I could say not with name now, but I say with label. And then this would be small. And then I could say here with label, and I can say big. Now we would get the equivalent thing. The cool thing about this is that now I could have, if I needed another processor, it would all be able to just using this labeling system. Okay. And you can see that runs through exactly the same. So there's a question here of when we use with name in the config for several processes, for example, FastQC and MultiQC, but then they only run FastQC, you get a warn upon execution. Is there a way to not get this warning? I will leave that one to Paolo. So the question is there a way to not get this warning when you are defining it, I think in the config, and then you don't actually use that with name inside that? Okay. And one that comes up very commonly is we want to use multiple containers for each process that we have. And this can be done exactly the same as we had before. So with name, so you have several options here. You can say with name, foo and bar, have some different container that we want. You could also define this actually in the process itself. So in the script itself, we could say, as before, this is like container, and this is like the foo container. And then I could have another container, which should say in Docker Hub, that was like bar. Okay, could have that in there. This is the equivalent thing of what we've got inside our with name. There's not much more to say, on that. It works exactly the same. So all we're doing here is just showing you a different way of using a directive process, changing the process directive, but now we're doing it inside the config with a selector. Okay. What's for sure the most important though, and most useful is profiles. So you can imagine that what's really annoying in all of this is that if I'm setting this process here, I'm creating this block, but this is essentially applied to all of my, every time I run this pipeline with this Nextflow config inside this directory, this is going to be applied. And this is maybe not so particularly useful for us because we don't want to have to change our Nextflow config file every time we change the environment, every time we change in a new location. If I share my pipeline with you and it contains a nextflow.config, I don't want you to have to run the config that I've got set up for my environment. So to do this and to allow the selection of groups of config from the execution of an Nextflow pipeline, we use what's called profiles. And profiles are extremely useful. Here's an example of where we have a profile. So we have a standard profile, which is executed every time. It's always going to use this. We can define a profile that we use for the cluster. So for example, I could have a cluster profile here, which is just going to use Sun Grid Engine, long queue, 10 gigs, etc. And then I could have a cloud execution. So I could have a cloud profile. And the good thing is that we can now switch between these profiles using the dash profiles from the command line. So you can see that you can say Nextflow run your script, and then we can change the profile, and that profile will be selected. So this is exactly what's happening with, you often see, there was a question yesterday about profile Docker. Well, Docker is simply one of these profiles that's been created for the NF core pipelines. We can see it as well in our example here. This is the RNA-seq example that we have. Here we have the profiles. We have standard, because we're always using this container. We have Slurm, which is a way of running this pipeline with Slurm. You'll use the Slurm executor with Singularity, with AWS Batch. And the nice thing here is that we can also combine these profiles together. So you can run multiple of these profiles at the same time. Profiles are really useful, and we use them a lot, both in NF Core, also in Tower. So just to show you again this, but this should hopefully make a little bit more sense. Now, if I was to go into Tower and launch my pipeline with that, one of the options that we have, instead of being able to having to put all of your config inside of here, I'm going to select the pipeline that we had before. And then from my config profile here, I could, for example, and this actually reads, the cool thing about this actually reads the Nextflow config file. So if it knows which profiles are available to me, you can see that all these are the ones that are available. If I to put, for example, S3 data in here, if I select this one, I could add another profile in here. I could put test. I can chain these together. They get overridden by the last one. So if there is a parameter, or if there is something which overwrites or is the same as one that's already previously defined another profile, it will write that over. But I'll be able to launch this, launch with S3 data in here, and now that's going to use this here. So it's going to use this container. These reads are already in S3, so this is something you might want to do to speed up your pipeline, and it's going to be using this this profile block. Okay. So there's a question here about what's the exact priority for the different configs are applied. So so I would assume that command line parameters are more important than config files, are more important than config in the workflow itself. So in terms of parameters, yes. So the parameters, that's exactly right. So the command line parameters take precedence over parameters defined in the config file, which take precedence over the ones in the workflow itself. That's exactly right. But what is done if we have conflicting definitions in a conf file, like both a label and a name match on a single process? maybe I answered this before, but if we define several configs, like for example, imagine that we have, in this case, standard and then cloud. So this is going to run standard and then cloud. You'll notice that, imagine that these were different. So in this case, because cloud is named second in the profile, it's the second one that we list. We just listed standard, then cloud. The parameter will actually come from cloud. So the cloud one here, the params genome defined in cloud, will overwrite the one params.genome, because these are essentially the same. So I hope that answers the question there. Okay. I'm going to hold off on jumping into cloud deployment now, because I think we can look at that tomorrow, because it's a whole nother section in itself, and it'll probably be a bit messy if we start that now. But if there's any other questions on that, feel free to ask on anything we've seen today. So on the containers, on the Nextflow config, on how we get that set up. I'll be happy to take those. Otherwise, we're free to adjourn, and we can see you tomorrow for the last session. Awesome. Thanks, everyone.